Okay, so in this section, I will do a brief review of forces. Now, forces, again, obviously are a overarching theme. They tie in with almost every chapter we've seen. But this will go back to the basics, making sure we're hopefully pretty comfortable with the basics of forces. There are a lot of key questions that deal just with the basics. So we definitely have to have this section down pretty well. So we know the definition for force, right? Force equals mass times acceleration, right? Now they've defined it a little bit differently on our equation sheet, but we know that if there is a net force, right? So if there is a sum of forces, then there has to be an acceleration acting on the object. So a lot of concepts then tie in with this, right? A lot of things we want to make sure we're pretty comfortable with when we talk about forces. So first and foremost, if an object accelerates, right? So if the acceleration is not zero, then the net force must also be something other than zero, right? So if an object is changing its velocity in any way, because that's the definition of acceleration, right? Acceleration is a change in velocity over time. So if the object is changing velocity at all, speeding up, slowing down, changing direction, whatever it may be doing, then there has to be a net force, right? If the object has zero acceleration, right? So if the acceleration is zero, which would be either constant speed, so constant velocity, right, or at rest. So if the acceleration is zero, we're moving at either constant velocity or at rest, then we know right away that the net force is zero. And so that's really one of the foundations on a lot of these questions. If it feels like a forces question, kind of the first thing you need to ask yourself is it accelerating? Is the net force zero? Or is it not accelerating, right? So that's the big thing that you have to get down to. The other couple ideas that tie in with this, one, the acceleration and the force, the net force, always have to have the same direction, right? So the acceleration and net force will always be the same direction. They've got to be going the same way. So in other words, if I have an object that is moving from left to right, so it's sliding this way, but if I know that that object is slowing down, I know by the definition of acceleration that it must be accelerating to the left, and therefore there must be a net force going to the left. I know the exact opposite too, right? If I have a block and these are the forces acting on it, then I know right now, no matter what, it has to be accelerating that way if these are the forces, right? I'll just label those F1, 2, and 3. So it has to be accelerating to the right. That does not necessarily mean that it is moving to the right. And that's a common question. This was one on one of the tests earlier in the year. You had a question something like this, and they showed us maybe a frictional force going that way. And it asked us which way is the object moving, or which way is it accelerating, which way is the net force, right? We do not know which way this object is moving. We don't have enough information right now to know which way it's moving. The only thing we know for sure is it is accelerating to the left. It could be starting from rest and picking up speed to the left, or it could be moving to the right, and because it's accelerating that way, just simply slowing down. We don't have enough information, so be really careful. Forces do tell us a lot of information, but they do not always tell us the entire story, so don't assume anything that we don't know for sure, right? So if another common misconception question that pops up with forces, right? Can the force be non-zero when the velocity is zero? So can the force be something other than zero while the velocity is zero? Well, so can the force be not zero while the velocity is zero, right? Again, this is one that we tend to overgeneralize a little bit too much. A lot of students say, well, acceleration equals velocity over time. So if velocity is zero, then the acceleration would be zero, and the force would be zero, right? That's not quite true, though. Acceleration isn't velocity over time. Acceleration is a change in velocity over time. And there is a very big difference between velocity and change in velocity, right? The other example, the way that I would approach this is just think about a couple counterexamples for this. If I take something and I throw it straight up into the air, we know because we've done many times throughout the year that at the highest point, if it's been thrown straight upward, its velocity will momentarily be zero, right? But if it's in the air, the net force is not zero, right? The second that ball is in the air, the net force is the force of gravity pulling down. So at that moment right there, at the highest point, the force of gravity is not zero. It's pulling down with the force of gravity, right? But the velocity is zero. So velocity and forces do not directly relate. We have to be careful about, again, assuming too much, right? A few concepts to make sure you're comfortable with. Hopefully they make sense. Again, we'll practice those a lot, but when you're doing a force type question, be very careful because there's a lot of missteps that students take on those. So be very deliberate, be very thoughtful, be very specific in what you say, and just make sure we're thinking them thoroughly through, right, and answering as well as we can. The number one step to do when it comes to forces, right? So step number one, always, and really this is true no matter what, right? I don't care if it's forces or energies or momentums or anything else, right? The number one step that we usually want to do is identify what's the free body diagram for an object. So let's say that I've got a block on a table, and maybe the block is hooked up to a pulley system, right? So it's doing something like that. The first thing I'm going to do on each individual block, right, is identify what forces are acting on it. So in this case, there's a force of gravity going down. There's a normal force pushing up from the floor going upward. There's definitely a tension pulling off to the right. And then depending on the table, maybe it's a smooth table, maybe it's not a smooth table. We might also have a frictional force going that way, right? So number one step is always, always, always identify a free body diagram for that object, right? Let's do another example where maybe this block is on the ground and I'm pulling it with a force off at an angle, right? So what forces would be acting on this one? Once again, we would have a force of gravity. We would have a normal force acting upward from the ground. The normal force, however, should not, even though my picture is probably not the best, I'm going to change this real quick. The normal force should not be equal to the force of gravity in this case, right? We know right now that it can't be equal to the force of gravity because, now these don't actually belong on my free body diagram, but there would be a vertical component of the applied force, and that plus the normal force should equal the force of gravity, right? So be careful on that one. Another common mistake. And then maybe this one would also have a frictional force working against us, doing something like that. Okay, so number one step on every single one of these questions needs to be identifying the free body diagram, and then deciding from there, the big question you have to ask yourself again is, if the net force is zero, then what does that tell me about all of my forces? Well, it tells me that all of my forces horizontally, the sum of my horizontal forces and the sum of my vertical forces, each need to add up to be zero, right? So in each of these two cases, like in the first scenario on the left here, if I knew that the net force was zero, then I know very confidently right now that the normal force needs to be equal and opposite to the force of gravity. Similarly, I know that friction would need to be equal to tension, because if the net force is zero, those two forces have to be equal and opposite, right? Each of those pairs. Same idea in my second picture over here, right? If the net force is zero, then I know that my normal force plus the vertical part, so I'll call this theta, so plus f sine of theta, need to be equal to my force of gravity because the object is not accelerating up or down. And then horizontally, friction needs to be equal to the cosine component of that applied force as well, right? So that would be if I know for sure that the net force is zero. How do we know if the net force is zero? Well, maybe they tell us something, right? The key phrases to look out for: if it is a constant velocity, we know the net force is zero. Because if it is a constant velocity, we know that it is not accelerating. And if it is not accelerating, there is no force, right? And then the other phrase is simply, if it's at rest, we know, once again, the velocity is not changing, and therefore the net force is zero. Okay, so balancing forces isn't too bad. The other question becomes, well, what if it's not, right? So if the net force does not equal zero, then that tells me that not all of the forces are balanced out, right? So if I gave you a situation again like this, maybe it's pulling off at the angle, I've got the normal force going up, I've got gravity going down, I've got friction going this way. What if I said that this object is accelerating, right? It is accelerating to the right. So let's say that we know that the net force is accelerating that way. How do we approach these questions? Well, the big thing we need to do is we need to be able to set up our net force, right? So if it's accelerating to the right, we know the net force has to be going to the right. So then if I'm looking at this, I just need to make sure I'm thinking about which forces are working with me and which forces are working against me, right? So if I break this up, again, not actually on my free body diagram, but the cosine component of my applied force would be working in the same direction as my net force. So I'm going to go ahead and define that as being positive. And then friction is working directly against me, so I'm going to define that as being negative, right? The vertical components wouldn't have anything to do with the net force going to the right, and therefore we still know that the two vertical components going upward need to be equal to the force of gravity going downward. But this then gives me my starting point, and now I can solve for whatever I need to solve for, right? So the big question you have to ask yourself is the net force zero? Do I need to balance forces, or should I be setting up a net force like we've seen many times throughout the chapters, right, based on which way it's accelerating? And sometimes you have to decide which way it's accelerating first, or even if it's accelerating at all. So those are big questions for us. Tying in with like circular motion, if I gave you an example where this is a vertical circle, let's say there's a ball at the bottom of the vertical circle. Again, step number one, identify the free body diagram, right? What forces are acting on that mass as it's being swung around the circle? Well, again, if I'm swinging it vertically, I know that the force of gravity would be pulling directly downward. And if I'm swinging it, it's on some type of string or tension or whatever that may be. So there has to be a tension pulling upward, right? In this case, so again, the big question you need to ask yourself is, should the net force be zero? Should those two forces be equal and opposite? Or should the net force not be zero? Well, the answer with circular motion, the net force should not be zero, right? We know right now, 100% sure, the net force is not zero, because if it was zero, it wouldn't be changing directions. It wouldn't be moving in a circle. So the net force is not zero. So now the question is, which way does the net force need to be going? Well, again, if we're comfortable with our circular motion, we know that the net force is always going towards the center of the circular motion. Now, that's usually what we call our centripetal force. So the equation that I would set up for this would be the centripetal force equals which force is working with me? Well, it's tension, minus which force is working against me? It's gravity. There we go. Now I have enough to where I can start plugging in values or breaking this up in terms of the variables and the measurements they gave me, and now I can try to solve. Okay. Let's talk about a couple other ideas here with friction, just some of the other types of oops, I said friction, I meant forces, but some of the other types of forces that we've seen, beginning with friction, right? Friction is a very common force. We've dealt with it a lot, right? Friction, there's two types of friction that we've seen a lot of in this course. We've seen kinetic friction, which is the friction that opposes an object when it's moving, and we've seen static friction as well, right? The equation for kinetic friction is the coefficient of kinetic friction times the normal force, right? The equation for static friction is not always an equal to, so it's actually a greater than or equal to the coefficient of static friction times the normal force. So let's break these down real quick and just make sure we know what we're looking at here. So again, kinetic friction is pretty easy because it's always an equality. It's always an equal to, right, as we're solving this. So if I have a box that's sliding, if it's being accelerated one way or even just moving one way, I know friction, kinetic friction, would be acting against that motion as it slides, right? If I want to find the force of kinetic friction, all I really need is the coefficient and the normal force. So even if there's a force of maybe, let's say 30 newtons going this way, kinetic friction would be maybe 5 newtons going this way. Similarly, if that same box, maybe it doesn't even have a force going to the right, maybe it's just being pushed to the right, so the velocity is going this way, but there's no force going to the right, it would still have a 5 Newton frictional force working against it. So the force of kinetic friction never changes as we're looking at our forces here, right? That kinetic friction should be a constant until the object is either brought to rest, or obviously if it's already at rest, we're not using kinetic friction. Static friction is the one that's a little bit trickier, right? Static friction is the one that tries to prevent an object from changing its state of motion to begin with. So static friction, again, that's why we have the inequality involved. If I apply a force of 10 newtons this way, and the object is not moving, then I know simply that static friction must also be supplying 10 newtons of force the opposite direction, because the only way that the object is not moving is if the net force is zero. Static friction can never exceed the force that I'm applying if the object is remaining at rest, right? That doesn't make any sense. If I'm pulling 10 newtons to the right and static friction is 15 newtons, then all of a sudden the box would start shooting the other direction. That just doesn't make sense in reality, right? We know that that doesn't happen. So instead, static friction simply matches what it needs to. So now maybe I am applying 15 newtons of force, and now, hey, maybe static friction can supply 15 newtons of force. right? That's going to continue up until a certain point, which would be the maximum value. So let's say 15 newtons was the maximum value for static friction. So now if I apply 20 newtons, static friction is no longer enough to prevent that. So the box will begin to accelerate to the right, and therefore kinetic friction will come into play. And now we can work with kinetic friction instead. Okay, so basics of friction. I know most of us are pretty good with friction. The big tricky concept, though, is the fact that, again, static friction only matches what it needs to. So when you're calculating static friction, be very careful about just plugging into this equation, because you're going to get a number, but we might not necessarily need the entire number for static friction, right? So if I find out static friction can be 20 newtons, I don't necessarily need the full 20. You have to pay attention to the context and decide if you do. The other last part about friction that can be a little bit tricky, we know most of the time friction opposes the change in motion. Most of the time friction's opposing the motion of the object. But that's not always the case. So let me give you an example here. What if I have a truck? It's a beautiful truck, I know. Right, so I've got a truck with like a nice flatbed here, and I have a box that is resting on the back of that truck. As the truck accelerates this way, do a free body diagram for the crate. So if I do a free body diagram for the crate, the only forces acting are the force of gravity and the normal force. And then there has to be another force though, right? Because if those were the only two forces acting, then as the truck pulls out, that box would still just stay exactly where it was. And now the box has fallen off the truck because the truck pulled forward, it stayed where it was, right? We know that obviously in reality, most of the time that doesn't happen unless maybe this guy's really flooring it, right, and taking off without his luggage there, right? But in this case, what force is actually causing the crate to move with the truck? Well, the force that's actually doing that is the static friction between whatever that crate is and the bed of the truck. So static friction doesn't necessarily oppose motion. In this case, static friction is what's causing the net force. It's actually what's causing us to accelerate off to the right with the truck. So every once in a while it does get a little bit tricky. So just be careful about assuming too much when it comes to our forces. And then finally, as with many of these topics, I do want to tie in with graphs just a little bit here just to make sure we're comfortable, right? So with our graphs, the big thing we have to be comfortable with forces is realizing that forces relate directly or proportionally. Sometimes they use this little symbol for proportional, but I know that gets confused with alpha. So forces relate proportionally to our acceleration. So in other words, if I can look at a graph and I know that the acceleration is 0, then I know that the net force is 0. If I can look at a graph and know that the acceleration is not 0, then I know that the net force is not 0. So let's look at an example or two. So let's say that I give you let's do a simple one. Let's give you an acceleration versus time graph, right? So if I gave you an acceleration versus time graph and it looks something like this, and I asked you where on this graph is the net force 0, well then I just simply look at the graph. The only time that the acceleration is 0 is down here, and therefore the net force would also be 0, right? At these 2 points up here and here, those 2 segments I should say, right? The acceleration is not 0, and therefore the net force can't be 0 either. Let's look at a tougher example. Let's go to velocity versus time. So what about this, right? What if I give you a velocity versus time graph that does something like that? Well, how do we find the acceleration on a velocity versus time graph? Well, acceleration is change in velocity over change in time, which is my slope. So the acceleration is the slope of this graph. If the slope is a non-zero number, this would be a positive slope, and therefore it would not be equal to 0. Then that tells me that this should have a net force that is not equal to 0. So in this case, the velocity, as the velocity is increasing, the net force cannot equal 0 because otherwise the velocity should be constant. What if the graph then leveled out? Well, if this slope is equal to 0, then the net force should be equal to 0 because the acceleration would also be 0. And then finally, probably the trickiest graphs, but maybe the most important ones to translate, right, are our position versus time graphs. So what if I give you a position versus time graph that's doing something like this? Well, the slope of a position versus time graph does not equal the acceleration, it equals the velocity. And if the slope is constant, so even though it's positive, it is positive, but it is constant, it is a straight line, and therefore the slope is not changing. And since the slope is not changing, that means the velocity is constant, And if the velocity is constant, that means the acceleration is 0. And if the acceleration is 0, that means the net force is 0. Similarly, if I gave you a position versus time graph and it looks something like this, that tells me that the velocity is 0. And because the velocity is remaining at 0, not just because it's 0, but because it's not changing from 0, the acceleration is also 0, which means the net force is also 0 as well. And then finally, how do we actually tell if there's a net force on a graph like this? Well, it would look something more or less like a curve. So think about this graph, right? If this were my position versus time graph, then the slope starts initially pretty low, which means the velocity is positive, but it starts pretty low here. And then as I go further on, the velocity, the slope, is getting steeper and steeper, which means the velocity is now getting more positive. I'm just going to indicate it like that. Now it's even more positive, so the velocity is in fact changing because the slope is changing. If the velocity is changing, the acceleration does not equal 0, and therefore the net force does not equal 0. Okay, so this is just a touch of what we have to do for forces, right? We know that forces are very involved. We know that we've seen forces throughout the year. Again, hopefully this is a nice review of the basics of forces, but these are the skills that we have to have mastered if we want to be successful with most of the other sections as well. So again, spend some time. Let me know if you have questions. Hopefully as we practice more, you'll see what things you do and don't need to work on a little bit more. Just don't hesitate to let me know.